Okay, kia ora everyone. Today we're doing the Level 2 Chemistry Reactivity paper, Acids and Bases, from 2020. So first question here, we have sodium hydrogen carbonate dissociating into ions as a salt. So we need to recognise that we've got a sodium ion in it and a bicarbonate ion. One-way arrow because it's a salt. Na plus HCO3 minus. Dissociation. Okay, one of these things is amphib product, that's this. How can it act as an acid and a base? HCO3 minus plus water. So they're both going to start off that same way. Okay, both starting off the same way. Equilibrium arrows because it's a weak acid or base, and when it's an acid it needs to be forming H3O plus and donating a proton. Change the sign, remember, so it's balanced, and over here as a base it's going to be forming OH minus and it's going to be accepting a proton. Okay, pH of 11.8, what is the concentration of OH minus? Right, so a couple of ways you could approach this. One way is to go concentration of OH minus equals 10 to the negative POH. So we just need to calculate the POH. We'll do that by going 14 minus 11.8. So pH plus POH is 14. So the POH is 2.2. If we put that into this formula here, we get 10 to the negative 2.2. So the concentration of hydroxide ions is 6.31 times 10 to the negative 3 moles per litre. Okay, ionization constant of water varies with temperature, and the pH is at 0, and the dissociation constant, so the dissociation constant is not 1 times 10 to the negative 14 now, it's changed. How do we work out the concentration of these? Okay, so we need to recognise that these are going to be the same. Okay, and we can use that to calculate the pH if we can work out the H3O plus. So H3O plus squared equals 0.114 times 10 to the negative 14. So therefore H3O plus concentration equals square root of the KW. There. So let's put that in our calculator. Square root 0.114 times 10 power of negative 14. We get 3.376 times 10 to the negative 8. So that's the concentration of H2O plus. And we just go pH equals negative log H3O plus. Negative log answer. pH equals 7.47. Alright, next question. pH of 3 basic solutions, sodium ethanoate, ammonia, sodium hydroxide. Explain why they have different pH values yet the same concentration. Okay, so different pH but same concentration. We're thinking dissociation here. Sodium hydroxide has got the highest. So what do we know about sodium hydroxide? Well, we're going to say NaOH is a strong base. What does that mean? It means it fully dissociates. Okay, and we're going to show that by going NaOH equilibrium arrow, one-way arrow goes to Na plus and OH minus. Okay, so every 1 mole of this produces 1 mole of this. And that's why if you do the calculation in here, that you're going to get pH of 13 for every 0.1 mole per litre sodium hydroxide. Secondly, moving down, NH3 is a weak base. So NH3 plus H2O, equilibrium arrow this time, OH minus plus NH4 plus. Right, partially dissociates less OH minus or lower OH minus concentration. Okay, and then finally the sodium ethanoate, we need to recognize that this is a salt, CH3COONA, that dissociates in water. So the two-step reaction, CH3COO minus plus Na plus, and then this thing reacts further, CH3COO minus plus H2O, equilibrium arrow this time forms OH minus and CH3COOH. But because of this lower pH here compared to the 10.6, we know that this reaction here must dissociate less than this reaction here. So we just need to say that at the end as well. CH3COO minus, the ethanoate ion, is a weaker base than NH3, hence lower pH. Okay, so it's all to do with dissociation. Fully dissociates, partially dissociate, but this dissociates more. And this is a salt. Okay, we've got a rate of reaction question here. Potassium permanganate going from purple to clear, colourless, after 45 seconds at different temperatures. We can see that this reaction has proceeded the furthest because it's gone the clearest. This has still got some purple in it. This is in the middle. So what we're saying here is obviously that rate of reaction can affect the, or the temperature can affect the rate of reaction. And if the temperature is affecting the rate of reaction, we need to justify how that works. So the 60 degree is furthest to completion. 20 degrees reacted least. Okay, and we need to talk about collision theory and activation energy from our answer. Okay, so let's say in the 60 degree test tube, what's going on? First of all, more heat energy. This leads to more kinetic energy of particles. Now, this means that they're moving faster. Now, if they're moving faster, they're more likely to collide per second. More collisions per second, or greater frequency of collisions. Okay, but the other point as well is when they do collide, they have greater energy. Okay, which means that more particles are above the required activation energy. Okay, so make sure that this is two clear points. Okay, moving faster, so there's more collisions per second, but also the collisions that do happen are generally above the activation energy. Now, these two things combine to lead to more successful collisions. Okay, and they'll be observed in this case by the solution looking clearer. Okay, this next question here. We're looking at concentration of the acids. This is going to be just a nice little bit of calculation to start off with. We're going to be using these two equations here. So calculating the H3O plus is 10 to the negative pH. So 10 to the negative pH, 0.89, is 0.12. Now it says 88, so round it up to 9. All right, and then next question, we're doing it the opposite way. So we're trying to calculate the pH using this formula here, negative log concentration of hydronium, 0.0158. pH is 1.80. That makes sense. Look, we've gone less hydronium, so the pH has gone up a little bit. So here we're expecting this answer to be slightly smaller than that. We're following that pattern. So we're going to go 10 to the negative 2.94, 1.158 rounds up the 4 to 5 times 10 to the negative 3. So yeah, we're getting smaller as we go because the pH is going up. Okay, we're adding calcium carbonate to each of these solutions. The volume of acid is the same. Identify which solution have the highest rate of reaction. Okay, so calcium carbonate's a base, so it's going to be an acid-base reaction. And what's going to happen, like which one's going to be the fastest? Well, obviously the highest concentration of acid is going to be the fastest, okay? So what we need to say here is that in the same volume, the higher concentration will have more acid particles. Okay, and these react with the calcium carbonate. More collisions per second, faster rate of reaction. Simple. More particles of acid, increased chance of collisions with the calcium carbonate, so therefore more reactions and faster rate of reaction. Okay. Compare the electrical conductivity of hydrochloric acid, HCl, with a solution of ethanoic acid, CH3COH, of the same concentration. Use equations to support your answer. Okay, key here is we're talking about electrical conductivity, and we're told that they're the same concentration. So when we think electrical conductivity, we're thinking free moving charged particles. Okay, that could be electrons or it could be ions. In this case it's going to be obviously ions. Okay, and they're the same concentration, so how are they going to form ions? By dissociating. Which is the better dissociator? Well, we should recognize that this is a strong acid and this is a weak acid. So we'll use equations to support our answer. HCl plus H2O, one-way arrow forms H3O plus, and Cl minus. Okay, so for every mole of this we get 1 mole of this, which means that the there's more ions, 1 mole of this and 1 mole of this, whereas for the CH3COOH, the ethanoic acid, when that reacts with water, we get an equilibrium arrow this time, and that's forming H3O plus and CH3COO minus. So for every 1 mole of this, we're getting less than a mole of this and less than a mole of this. So the point here is fully dissociating. In the case of HCl, because it's a strong acid. Partial dissociation. Partial dissociation of CH3COOH, ethanoic acid, because it's a weak acid. More ions to carry charge. Better conductor. Okay, so there's more ions being produced in the strong acid solution than the weak acid solution. Ions are what you need to carry electrical charge, therefore the hydrochloric acid is a better conductor. Alright, moving on to question 3. Write the equilibrium expression for gaseous carbonyl fluoride. So okay, the Kc, this is the equilibrium constant, just shows us whether the equilibrium lies on the right or left of the equation. So we're just going to write this here, Kc equals concentration of these things divided by concentration of this thing here. Now just remember that we've got a 2 here, 2 moles of this to 1 of this and 1 of this, so we need to put that into our equation. We can put that in with a squared up there, okay? Now, next question. We're actually going to do the calculation now. So they want us to calculate the Kc when that is at that, and both of those are at that. Alright, so just going to put the values in. Kc equals this times this, and we know that both of them are 0.8, so we just go 0.8 squared over concentration of this one, 0.04. Now that has to be squared as well because of the formula equating for the mole ratio. So quite simply, it's going to go 0.8 squared divided by 0.04 squared, 400. Alright, so the Kc for this reaction here is 400. Alright, different temperature, Kc value is 50. What does that indicate about the extent of the reaction? Okay, so what's important here is that a big Kc, or above 1 really, a Kc above 1, so let's write 50 is greater than 1, therefore we're making more stuff on the right hand side, okay, more products being made, however not as much as up here. Right, so this reaction is going to still be favouring the products, but not quite as much as actually at the temperature that we were doing this equation at. Okay, enthalpy change is negative 24 kilojoules per mole. Okay, so we're thinking this is exothermic. Okay, this means it's giving off heat. This reaction is producing heat, releasing it to the environment. What happens to the Kc when the temperature is decreased? Okay, so a decrease in heat means the reaction will want to go in the way that produces more heat. Okay, so try and balance it out. If you're losing heat, the reaction will try and want to produce more heat to balance out those changes. Okay, we know that the Ford's reaction is the exothermic one. Okay, we can see that from here. This is negative. Ford's reaction is exothermic, so therefore the Ford's reaction will be favoured. Okay, and if we're favouring the Ford's reaction, what happens to the Kc? So if you're making more stuff on the right hand side, more of these, this Kc is going to go up. So therefore, increase in Kc. Alright, we've got 3 different examples here of what happens when we mix Fe3+, SCN-, and we form this complex ion here. It's an equilibrium. The Ford's reaction produces heat, so we've got heat on the side. What's going to happen when we add more potassium thiocyanate solution to the mixture? Okay, KSCN. We need to realize here that this is a potassium ion and a thiocyanate ion, and that thiocyanate ion is a common ion, right? So we've got a common ion principle going on here. So increase in the concentration of SCN means that this reaction will try and restore equilibrium. How can you do that? How can you restore the equilibrium? Well, you can try and use up the excess SCN. So using up the new increase in SCN, and therefore reaction drives to the right, okay, favors the formation of more FeSCN2+, okay, and because that is dark red, they want us to say what the effect on the colour is, so we're going to say reaction becomes more dark red, becomes dark red or more dark red, okay, because this is a common ion issue. Common ion effect. Okay. Solid sodium fluoride is added to the mixture. The F ions react with the Fe3+ ions. Right, so just looking over here, if we add something in that is going to react with the Fe3+, the concentration of Fe3+ will decrease. Okay, the reaction will try to restore equilibrium. And it's going to do that by making more Fe3+. Therefore, the reaction drives to the left. That means that it's making more Fe3+, and it's using up the FeSCN. Okay, therefore it goes more orange. Okay, we lose that dark red colour, becomes more orange. Okay, and finally, a test tube containing the reaction mixture is placed in a beaker of recently boiled water. Okay, so like we said before, the Ford's reaction is exothermic. Ford's reaction is exothermic. If we add more heat, when you increase the heat, the endothermic reaction will be favoured. Okay, so the reverse reaction will be favoured to the left, and that means that more Fe3 plus is made, and the reaction looks more orange. All right, that's us.